start the recording. Let's see here. Let's see. Admit everyone. Oops, that's not what I wanted. That's not what I wanted either. Now I can't tech for some reason. Oh, stop share. That's what I want. All right. Howdy, folks. Apologize for that little bit of technical difficulty that I ran into. But I'd like to welcome you all to Evening Under the Stars, a public event series that we host here at George Mason University. And what we do is we invite astronomy professionals or folks in the astronomy adjacent community as well, reporters, that sort of thing, science communicators, here to give us a public talk. And then following that, we present a tour of our observatory that we're very proud of. In the before times, we would do this in person, but now because of the pandemic, we are doing things virtually. Hopefully we can get back to doing it in person, but one of the advantages of the virtual experience is now we can ask speakers from all over the world to contribute to our public talks, and they don't have to travel very far. So where we're doing, or where we're located, we're looking obviously at George Mason University, and we have our observatory is attached to Research Hall. Our observatory is attached to Research Hall. As you can see, it's on that silver tower that's on the back side of the building. And if you go to the roof, there is a white structure, which is our control room. And we're able to control the telescope from that room, or actually, as we're going to do tonight, virtually from really anywhere, but we typically do it from the university itself. Surrounding that image, you can see hopefully the images that we have taken here at the observatory, color photos of galaxies, nebulae, star clusters, and the like. And we are continuing to update this gallery of images. Our student organization, Friends of the Observatory, they are actively interested in astrophotography, and they are constantly providing new and interesting images for this gallery. As I said, this is the Evening Under the Stars, and for the spring, we are doing this alternating Tuesday evenings. We have two more events that we're hosting this particular semester. One is in April 16th, and the other one is April 26th, if memory serves. Although I may have those dates slightly off by a couple of days, but approximately April 16th and 26th. And as I described, we have a 30 to 45 minute talk followed by a 30-minute guided tour of the night sky. And thankfully, the sky seems to be actually cooperating with us today, thankfully. So we're actually going to open up the dome, and we're going to use a telescope to take images of the night sky as it currently is. If you're interested in what we do here at the observatory, if you're interested in the research that we do here, or the student research that we do here, the public outreach arm of our observatory, if you're or just interested in astronomy in general, please sign up for our free newsletter at the website listed. It is the Moon, the Mason Observatory Outreach Newsletter, and we update this every month. If you are interested in supporting us in a more, shall we say, substantial way, we would ask you to become a patron of the observatory. Dr. Plavchan and I, the director, and I are greatly interested in expanding our outreach arm. And to do so, we need we need personnel, and we need material, and all that basically boils down to money. Not that I want to be e-begging, but if you want to be able to contribute to our abilities to go out into the community and spread our knowledge and our love of astronomy to, particularly to the more rural areas that may not have the budget or the resources to investigate astronomy in upon themselves, please feel free to become a patron. And you can do so at various different levels. You may notice that at the Nova membership, you might see a familiar name, a Dr. Rob Parks, as it were. So I do put my money where my mouth is. And so, but enough of the e-begging. In terms of the observatory, we are not a one-person show. We have Dr. Peter Plavchen as our director. Myself, Dr. Rob Parks, is the deputy director. Kevin Collins is one of our observatory graduate students. Tonight, the public tour or the telescope tour will be given by M. Thunyapong. And then we have Jonathan Salvana, who is the president of the Friends of the Observatory student organization. And also tonight, assisting us is one of our tour guides, our numerous tour guides, Andrew, and he will be assisting M in providing that public tour, private or public tour. So what I'd like to do now is to introduce our speaker, Dr. David Baughman, Dr. David Baughman, and he is going to talk to us about active galactic nuclei, or very active galaxies with supermassive black holes in the center of them. David was part of the GMU community and still doing active research with one of our professors here. So, Dr. Baughman, if you'd like to come on, and I will stop sharing my screen and allow you to take over.
All right, thanks a lot. Hi, everybody. So I'm going to be giving a talk on just some general background stuff regarding, as Dr. Park said, hold on, let me get this to, so hopefully everybody can see the slides there, the title slide.
Yes.
Great. So I am going to be giving initial outline and brief background on just kind of what's the state of kind of what we're talking about here, kind of the overarching things that we're doing in the research community, how we're doing them, what we're looking for in order to kind of investigate these big, massive black holes in the center of these galaxies. And then we're going to just kind of talk about some of the research briefly that I currently conduct along with my former advisor, Dr. Peter Becker, who's still professor there at George Mason University. The research we have, it's pretty exciting to us, but I'll speak to that pretty briefly as I don't want to get this too scientific, as this is just kind of a talk for the general population. So next slide. All right, so just some general background about, kind of black holes and observational X-rays for black holes. You can see there, actually, many of you have maybe seen this in the news in the bottom left corner a few years ago. That is an actual quote unquote image, and that's using not X-rays, actually radio waves of a center of a galaxy called M87, and very massive galaxy. It's very big, and they used radio waves to see that quote unquote see that image. Detect that's basically an accretion disk around the black hole. So the antenna they used was about, you could call it the size of the planet Earth. Whereas when you're listening to your radio waves with your, FM or AM station in your car, it's a tiny little antenna there. In order to get this, they had to use a telescope that really, use multiple telescopes to kind of make itself the size of the planet Earth. So that's how hard it is to get these kind of images from so far away. But that's pretty cool. That was kind of the first quote unquote image we had, and that was a radio wave, just kind of give you a feel for what we're talking about. But that aside, much of the accretion disk knowledge that we have in the last 40 years has come from utilizing X-ray telescopes. Our atmosphere is really good at blocking X-rays. I'm sure everybody's familiar with the concern with X-rays in the doctor's office. And so, you might gather that our atmosphere blocks most of the X-rays coming from outside of, Earth. And we actually didn't even realize that there were a lot of X-rays happening until we were able to launch a telescope, and we were actually looking at the moon, and we saw, some other stuff, and we were able to see that there was just a massive amount of X-rays being generated around the entire universe that we can see. So in that bottom right image, you can see this is a plot of basically our universe that we see and the X-rays. And you can see kind of the bigger dots have more X-rays. So that was from 1999. And then there's another one from 2021. And you can just see that, really that this is constantly ongoing. Thousands and thousands of X-ray sources now are known. And many, many telescopes we've now launched into space and are continuing to launch into space, both not only in the United States, but in Europe. So there's lots of research that's going on. The reason that we have to use X-rays and higher energy, so X-rays are really high energy, right? So if you see there on the top right image, you can see all of our spectrum of light that we both can see in the visible in that small section right there where my arrow is, down to infrared, up to UV, talk about UV rays and getting that from the sun, right? And potentially getting skin cancer, so needing to use sunscreen, all the way into X-rays, which we use for a lot of medical diagnostics. People are familiar with X-rays, then all the way into gamma rays. And so one of the things about black hole research and is that black holes are very, very, very high energy creation objects in the universe. In fact, the most high energy, basically. And they're creating this high energy due to the massive gravitational forces that are occurring and what's happening around them. And so we get these high energy electromagnetic waves, and we are able to really understand what's going on with them by studying these higher energy aspects of them. And then, now more recently is radio wave astronomy is really finding out some interesting things but they had to go to the telescope that's quote unquote the size of planet Earth, right? So so that's kind of why X-ray astronomy has been utilized and how it's kind of grown over the last 40 years. So next, so what are we actually studying when we're studying black holes? Well, we're not studying black holes and for what would be called a quote unquote naked singularity. A black hole by itself would never really be able to observe that. We can observe that through potentially light interacting with it. So it's always by the implied of that there's a black hole. So maybe light is being bent and we say, well, there must be a black hole around there, but that's much harder to detect. In general, when we're looking at these large galaxy centers that we call black hole sources and AGNs, active galactic nuclei. So it's really just the center of the galaxy. What we're really trying to study is all of the stuff that's happening around the black hole that we can see that's generating all of these X-rays in the case of X-ray observational astronomy. So so again, so you've got these massive gravitational sources, these huge, massive galaxies that are 10 to the 8th solar masses, right? So they're absolutely enormous in terms of size. And so they've got all secreting matter around them that's generating these high energies. And then what we can do is we model those with different, basically we utilize equations that include gravitational effects, hydrodynamical effects, viscosity, radiation, all these different physical effects to try and model what's happening. And so on this slide, what you're seeing is kind of some different models of what we think might be occurring around the black hole in these AGN. So the key things to these, like I said, in terms of the accretion, it's really about accretion being the matter coming into the black hole, right? So how fast that's happening, the mass accretion rate you see there on the right graph there, that's a key thing. And also here on the left, this is basically your mass accretion rate. And so that affects what we think is happening physically with the black hole, as does, you can see this called optical depth. And optical depth is kind of how far you can see in to something. So, so for instance, our atmosphere, we can see through our atmosphere. So that has a very low optical depth. Clouds that you can't see through would have a higher optical depth. And so when we're talking about things that aren't necessarily, a huge solid thing, they'll have different levels of optical depth. So optical depth and mass accretion rate really are affecting kind of what the physics is and the theory that's developed to describe these, physical aspects of what's happening. And so the theoretical physics community has developed these theoretical models, and then those theoretical models are then utilized, and so they then utilize the different types of radiation as well that are happening. So I guess just really quick radiative processes, just really briefly, that these are the different kind of radiative processes that we think are creating the X-rays that we see. So there's black hole, there's black body to the upper left there, and that is many may be familiar with black body. Everybody has yep. And if anybody has a question, I'm just seeing in the chat, feel free to ask them here in the chat, and then I can answer them at the end of the talk. So for black body radiation, many might be familiar with that from their science classes in school. That's basically, it's kind of based on your temperature. It gives these nice standard quote unquote spectrum plots like you see here on the left, that we can actually tell exactly what the temperature is of that body radiating. Everything's got a black body that radiates based on what we see, what we observe in the spectrum curves. We can actually, there's a specific temperature. And then there's other types of radiations right there. Bremsstrahlung, known as braking. That's when you have electrons that are getting like stopped. They're getting slowed down quite a bit due to ions, due to atoms, right? Basically ions in a gas at a specific temperature. And then Comptonization, that's another one, but that's really where you've got photons and electrons interacting, either increasing the photon energy or decreasing the photon energy, depending on which way the transfer of energy is occurring. And on the bottom, you've got synchrotron and inverse. And synchrotron is a type of radiative process that that basically you have a particle that's moving really fast, and it's in a magnetic field, and it's spinning. And as it's spinning, it's radiating energy. So in general, things radiate energy when they accelerate and decelerate in magnetic fields, and that's what's happening there. So anyway, so there's all these radiative processes. I apologize, I just went down too much of a rabbit hole. But this is kind of gets to some of the physics that we're trying to understand in terms of what's causing the radiation. So so now we use these theories. So these are the theories 2 slides ago. These now we work with observational astronomy. So these are kind of four of the main categories of how we are trying to understand what's going on for these AGN. And I'll also just add, it's not just big AGN, right? It's not just big active galactic nuclei. It's also what we call galactic black hole sources, which are smaller black hole sources. You know, so there's black hole sources of all sizes. There's black hole sources that are just, you know, kind of tens of solar masses that are really tiny. There are black hole sources that go all the way up to these 10 to the 8th. So that's you know, that's basically a, you know, billion solar masses, right? It's huge. It would engulf our entire, I mean, it's, yeah, our entire solar system for sure. It's just very big. So then we use these different investigative techniques to understand all of these different black hole sources. So a light curve is a pretty straightforward one. For a light curve, we're just really looking at kind of the intensity of the light and how it's coming in. So if you just even looked at a, you know, somebody kind of, I guess, driving a car towards you at night and that light got brighter and then they kind of, you know, pulled in reverse and they kind of did something like that. That's kind of what we're looking at for light curves. It's just kind of an intensity of the light and how it's changing with time, because everything's always changing. Although there is a kind of a steady state as well. And then you see over to the right there, something called PSDs and QPOs. I won't go into those. That's basically just looking at other aspects of the intensity that we see of the light. Spectral states on the bottom left. So this is looking at, for the spectral states, this looks at both the actual narrow band kind of atomic line spectra that occurs, as well as broadband spectra. And so this one, you know, you could equate to, there's spectral states for anything you see will have, like in life, you see a flower and it has yellow, right? It has or red. So the different colors, you know, kind of are part aspect of a spectral state. So that's what that's kind of looking at. And then on the bottom right, there's another interesting thing that we look at that are called time lags. And so for the time lags, this is something that we're going to talk a little bit more about. This is the research that we are conducting. And it looks at how for a specific black hole source, you'll have different energies coming at you, right? So maybe, and this, in the X-rays here, you'll have both a maybe a 1 keV, so that's an energy level, and then you'll have a 10 keV energy level, and those energy levels will demonstrate and display a similar behavior, but they'll have a time difference between the two of them. So there's a correlation between what's happening between these two different energy levels of X-rays coming at us, and they display some interesting behavior sometimes. So that bottom there is a time lag for a black hole binary called Cygnus X1. But so what we're going to be looking at is active galactic nuclei for the most part for time lags. And one of the reasons that we look at the bigger sources is that things happen on much slower scales than smaller black holes. Because they're so big, everything takes longer to occur. And so we can actually understand things a little bit better depending on what we're looking at. Sometimes we like to look at the smaller sources for certain things, but for instance, for time lags, we usually like to look at the more huge black holes. Okay, so hope that wasn't too scientific. Going to get a little bit into mathematics here, just really quick to understand what Fourier lag is. So a cool aspect about Fourier transforms, some people might be shaking their heads if they've had this in math, but it's a really cool thing in the sense that every signal actually can be broken into its Fourier domain. And what that means is, so for instance, my voice is made up of a whole bunch of different tones that are generated by my vocal cords. And all of those tones are their own frequency, right? So each one of those frequencies are the composite of what you're hearing. And so in this case, for electromagnetic energy waves, it's the same exact, but with EM waves. And so you can see there in that picture, in the time domain, you know, it's made up of a whole bunch of different frequencies is what that's trying to demonstrate there on the left. And then what you can do is you can pull those apart and look at a specific frequency, and you can actually understand the signal by that specific frequency that's creating that composite frequency in the time domain that you're hearing. And so for these lags, like I said, what will happen is you'll have a lower frequency here. If you can see, follow my cursor on a certain lower energy, and then that might demonstrate something. And then what this is trying to show is that there's a lag between the two different times. So these times are T0, T1, T2. So there are different, you see the same similar behavior occurring between these two energies of the X-rays. And they generate these interesting plots that we can then go back and theoretically try and replicate, try and duplicate with our models. So one of the key reasons we have to do this is because the timescales are short, and so you can't really necessarily always just utilize that time domain to understand things. So you have to kind of break it into its frequency domain. So for instance, you know, we are pretty positive we have a black hole called Sagittarius A at the center of our galaxy, the Milky Way. And you know, when we're trying to understand right around the black hole, which basically is, so 1 RG is a gravitational radius, and that's, you can see there, I'm trying to stay away from equations, so I apologize, but basically, when you're talking about really close to the black hole, that time, even for our Sagittarius A, is only about 20 seconds. So again, these are really far away, you know, so far away that, recall that for the human eye, for instance, our human eye can only see out to about 5,000 light years, and our galaxy alone is 100,000 light years across. So when we're talking about looking at other galaxies, they are so far away that it's really actually phenomenal that we can even see any of these photons coming in at any of these energies. It's they're just so far away. And so that second to last bullet is that it's just, there's not many photons coming in, so we really try and need to use as many creative ways as possible to understand what we're seeing. And so that's what that's also, this helps us do this. We can just look at the specific frequencies. And so anyways, all right, so moving on. So there's two types of lags. There's the hard lag, and this is pretty easy. It's just basically the hard energy photon, that maybe 10 keV X-ray energy photon. It comes after the soft energy, the 1 keV. And what we think is pretty much one of the models, there's always different models, but one of the theories is that simply what's happening is for the soft, the 1 keV photons, they bounce around lesser times before they escape basically into, you know, deep space and come travel toward us, versus the hard photons, which we think would bounce around more often, just from statistical purposes, would be bouncing and scattering around more before they finally exit and come to us. So that's what we think is happening for hard lags, for instance. There's also soft lags, which where the softer energy, the 1 keV, so this might make sense to a lot of people, right? So a soft photon just pops out, and the hard photon just takes longer and pops out. So you can have the opposite happen, where you can have a soft lag, where the soft photon actually pops out before the hard photon. So the softer energy is actually coming at us before the harder energy. And so there's different models that have been out there trying to understand what's going on with this. So one model that's pretty well established in the community currently, this all happened about 10 years ago, so this is all pretty recent stuff, is they think that you've got this corona surrounding a black hole. So kind of, you've got the black hole in the very center, and then you've got a corona around it that's got a bunch of high energy in it, generating initial kind of source energy X-rays. And they think that what's happening for the soft lags is that there's just simply a delay that's occurring, where the energy of the 10 keV pops out, and then it goes off to a cooler kind of accretion disk around the corona, and then it actually hits other photons that then just pop out. And those are what's happening, is you have this delayed due to time. You have the high energy photons coming, hitting an accretion disk that's cooler and popping out lower energy photons, and that's why that's occurring. There's another one here that I won't go into. It has different, more complicated approach. And there's all these kind of different complicated geometries that people try to utilize to explain what's happening for these lags. All right, so what we did was we tried to go and see if we could understand it or create the lags with a much more simplistic, just physical equation that doesn't require a bunch of different geometries or extra explanations. And it's just very much, back to basics. Can we just generate this utilizing known physics? And so what we did was we are looking at, like I said, that Comptonization. So that's when you have the electrons and photons generating, giving each other energy back and forth, depending on what's happening in terms of the accretion rate and everything that's occurring. And so what we looked at is if you could have, there's different types of comptonization. I won't go into it, but there's bulk comptonization. Well, I'll go into a little bit. So bulk comptonization is kind of that, it's kind of, you can think of the whole thing kind of flowing in together, this bulk kind of comptonization, whereas thermal is comptonization occurring based off of the kind of temperature. And so basically what we said was, can we using comptonization as well as, kind of solving for the flow of the accretion rate, can we generate these soft lags? Okay, so one thing to note is that there's been a lot of evidence for, there are variations based on the accretion rate, as well as the optical depth. Like I said, those are kind of the key contributing factors to the different physics that we think is going on. But what we do know is that in general, there's been a lot of scaling laws that have shown that, this is important. It might be, you might say, of course, I think the same physics is happening no matter the size of the black hole, but it's something we still have to prove in the community, right? And so there has been a lot of demonstration that there is the same physics happening. And that's really all this slide is showing, is that the same physics we are pretty sure is occurring at all different sizes of these black holes. And so that's important to understand, so that we know that if we can demonstrate it for a certain size, we think we can demonstrate it for other sizes. So, all right, so we looked at one specific, so far we've looked at one specific AGN, active galactic nuclei. It's called 1H0707-495. And this is just kind of some statistics about it. This is kind of just showing you some data regarding it. It's 181 megaparsecs away, we think. It's 2 × 10⁶ solar masses. So it's about 2 million times. This AGN is about 2 million times the size of our sun. Yeah, and here's kind of an example of this is kind of a holistic example of what people think are going on with different with active galactic nuclei, and kind of you see there's these different names are just kind of showing, depending on what perspective you're viewing it at, it might appear as a different viewing angle, might make it look like something different, even though it's always the same thing. It just looks different depending on how you're looking at it. All right, so this is kind of where it exists, what we've looked at in the grand scheme of this red circle is kind of like where it is in our universe, where we're looking. That's an actual image of it. All right, and so getting to kind of the research that we've done, it is highly variable in the X-ray. It does show this. So this is showing the top right. This is showing those energies I was talking about. On the you can see they're on the bottom, and they're in keVs. So there's 1 keV right here where my arrow is, and then it goes all the way up here to showing you that there's about a 7 keV. And so this is just a plot of kind of the energy coming in that we're seeing. And then in the bottom left, you can see this is a plot of the, like I said, that just the standard understanding, like a time plot. So this is just that. So that's just looking at the actual X-rays coming in. And then on the bottom right, this is the lag plot that this AGN is demonstrating. So this is showing you again the lags where you'll have the softer X-rays, the softer meaning like the lower energy ones, 1 keV, say for instance, coming in at a different time than the hard lags. And so this is the plot that's done when converting that into the Fourier domain and looking at those lags. So you can tell it's a very interesting plot. It's not anything someone would expect, I think, just saying, hey, let's see what happens. And so one other thing to show about this one, AGN, is that it has, it shows an abundance of iron. And so iron is kind of the end of the road. It has, in terms of its energies, things kind of settle into iron. We're not going to get into the end of stars' lives or anything, but due to the kind of the energies and the energies that are occurring when atoms and molecules, when they combine and they fuse and everything, when that happens, iron is kind of the end of the road because it has kind of this low energy point. And so so iron pretty much is the end of the road. And so we expect to see a lot of iron, actually. And one of the things that we do see in this one, for instance, is that we see two different irons that are occurring. We see an iron line at 6 keVs and another one at 0.9 keVs. And those are important just in the sense that we can further understand what's happening and how much iron and how, and kind of the different processes. And so when we see those abundance of irons, that tells us something about what's happening with this black hole. And so finally to our results. So this is our theoretical results showing you the green plot there is actually what our theoretical model demonstrated when we write a bunch of code and we plug in that long equation that I had and we kind of work through all the math and kind of make that happen. That's what we've been able to generate utilizing kind of different parameters that we have expected to see based on observational data. And so the pink and the blue are two different observational data sets. And so, so you can see our model is pretty much well established that is doing that. And we have to have a kind of a source photon set. And so what we utilize as our source photons is that energy abundance of iron kind of creating the source photons to generate this lag. So we think this is showing you that there's potential that actually these abundance of iron photons, fluorescent iron, are creating along with this Comptonization that's occurring, which is one of those radiation processes simply, and that's what's actually able to create these lags. And so, so you can see there's the line. And so in conclusion, our theory is showing that with all this research that is occurring, there's obviously a lot of active research happening, but we feel like we are getting good agreement between observations and theory, and that potentially we're able to explain what's happening with our model, which is in contrast to other models that have been presented. And all this goes to, kind of the end state of understanding what's happening with these AGN and these black hole sources in general. This is an ongoing, very active area of research, only getting more active. There's still a lot to be had with black hole research, and there's lots of different ways that it's occurring now. So I hope that was at an appropriate level, and open the floor to any questions.
Okay, thank you, David. I definitely enjoyed that. If we could have a round of virtual applause for our speaker, that would be great. And I'm going to take sort of the director's or the host's prerogative to sort of comment on a few things and ask the first question of the night. I just first thing I want to do is I want to piggyback on what you were saying about essentially Fourier analysis, in that one of the things that I did was, and we as an and you showed an example of it, is basically image reconstruction. Is you can use interferometry to determine, make images of things like stars and black holes. And so the way I did it was the way I used the Fourier method was looking at getting data and basically breaking it into components to figure out the brightnesses of different regions and the contrast between different regions. So I just kind of wanted to illustrate yet another practice of how Fourier is used. As a minor note, my department, when I graduated from the Georgia State University, and there is a fairly large AGN community there. And so every time we had an AGN talk, there would be the exploding donut, where you have the torus and then the broad line regions and narrow line regions. So I was glad to see that that tradition kind of held true for that. I get my question is basically getting around to that. My question is, so you were saying, I'm familiar with reverberation as the mechanism for time lags because of reverberation mapping to get the mass of the black hole. But that's in sort of, that's in the longer wavelength regime, optical sort of thing. I didn't realize there was a question as to what was causing time lags in the X-rays. So what is the reason for why there are certain models, and why do certain models seem to fail, I guess, if that makes sense.
Why do they seem to? So I guess models are always good until they're proven wrong, right? I don't know why they seem to fail. I do know that I think anytime models need to start just adding to the, like anytime you take something that's nice and beautiful, and it's a circle, it's a sphere, and you say, well, this isn't quite fully describing it, so maybe we need to add a bump here and a bump here, and it starts to get ugly, right? And I guess from a physicist perspective, if the models all of a sudden takes 14 different additional things that you're trying to explain, whereas you might be able to explain it all with something that's much simpler, usually the simpler theory in my mind is kind of the way to go. So, but it hasn't failed. We were just wanting to see if there was a simpler explanation than what they're utilizing right now. And they've added to their model, and they're looking at different things, and but yeah, so.
So it's an Occam's razor sort of approach, where you want to keep it as simple as possible.
Fair.
Yeah, I remember using the name of it escapes me, that I remember using a bit of code where there were 24 individual parameters that you could tweak, and so my professor was like, yes, you can use this, and yes, you can get it to match your data very well, but depending on how many of those parameters you're tweaking, you have to really take it with a grain of salt. Because essentially, as a colleague of mine did, she looked at a light curve, and she actually can model that light curve very well by having an image of Santa Claus in his sleigh going across the surface of the disk. So I definitely understand where you're coming from. You want to keep it as simple as possible, because if you continue to add complications, then basically you can fit anything. So we do have a question from the audience. What is your favorite recent scientific discovery that contradicted earlier beliefs or earlier thought?
That contradicted.
Mm-hmm.
That contradicted. Well, I don't know if there's contradiction yet, but there's one area that I'm always interested to see advances in, that always concerns me, is the concepts of both dark matter and dark energy. Right now they're really still kind of these just it's got to have something to make it work. And there are a lot of ongoing research areas where there could potentially be explanations for both of those that don't require, again, collusioning a whole new physics. So that's somewhere where I'm always interested to see advances. And actually, there's actually was a recent advance on M87 about a year ago where they, I mean, it was less than a year, but they've now seen basically the results of the magnetic field with their radio waves. So that was great to see around M87. So I don't know of any solid contradictions in my recent mind where it was kind of a wow, aha. What about you, Dr. Park? Do you got any recent, like there was anything coming to mind that's a big contradiction?
Big contradiction. The not really a contradiction, but what I find is a lot of sort of recent discoveries are more along the lines of actually kind of the opposite of what we're talking about. You taking something that was pretty simple before and realizing that there's a certain amount of complexity in them. So for example, there is essentially a parameter which deals with limb darkening, or how the brightness of a star dims as you get to the edges of it. And before we essentially had two categories or two coefficients which explain these based on the physics involved. If it had a radiative outer layer, then it had this coefficient. If it had a convective outer layer, then it had this coefficient. But now that we can actually start looking at the surfaces of stars, we find that that's more of a continuum than we had previously thought. And so I think that in the area of recent discoveries, I think that's more in line. I don't think, I'm with you, I don't remember or can't think of anything that was a contradiction, but more just a...
Yeah, we seem to just keep getting supporting. I mean, and I would say actually for dark energy and dark matter, we're not getting that supporting evidence yet, but we are getting a lot of supporting evidence for things like gravitational waves. You know, we've been able to see, we've actually witnessed those now, and those have been predicted. And a lot of particle theory. It just, you know, we keep getting further supporting evidence that what we think's happening, you know, like for instance, the Higgs boson, and like this things are going, quote unquote, the right way for the standard model, you know. For instance, black holes have kind of been inferred for about 200 years. I mean, so people questioned, you know, and then they questioned Einstein, they questioned, and then we got observational data on it, you know, all of a sudden the research exploded. So yeah, physics seems to be a pretty strong science community in that matter. Yeah, in that sense.
Yeah, I would agree. I think that the normal process of science is really to confirm and build upon the sort of the paradigm or the current thoughts. But occasionally there are obviously crises. There are,
yeah, like for instance, we thought the galaxy was the universe. We thought the Earth was flat. There are absolute, you know, examples of that for sure. I'm just trying to think of a recent one.
I think for me, the most recent is actually as an astronomer, the most recent would be the great debate whether or not the galaxy comprised the entire universe, or whether or not the universe was far larger. And so Hubble was the one who, for the audience, Hubble was the one who provided the observations that answered that question, that the universe is far larger than it is now.
Yeah, you point out, you know, what you just said there. So that's actually the beauty of the science community, is that they don't really say anything for sure until they get a lot of evidence. So there's a lot of discussion about, you know, for instance, the origin of the universe, the first 100 seconds, what exactly happened, right? And there's still a lot of debate going on. There's a lot of excitement, obviously, with the James Webb Space Telescope. I'm really excited about that. When that thing comes online, that'll be amazing. Some of the stuff we're going to get. So if you're not familiar with the James Webb Space Telescope, I urge anybody on this video to check it out. It was very expensive. I actually kind of had a play in it in my own career. So
nice.
that's, that's kind of, it's a long time coming, but I think it's going to be pretty exciting. And I think in general, the science community and the physics community for sure kind of debates things until they kind of go, okay, we've got some evidence now. All right, so this must be right. So, yeah.
So do you think that we're kind of on the cusp of another crisis, in the sense that uh, if we do find more evidence, and this is very speculative, but if we do find some more supporting evidence on certain ideas of what dark energy and dark matter are, do you think that relativity will essentially be overturned at some point?
No, I, I gotta say there, we've done some really, really exquisite scientific experiments, and recently we actually, there was a spacecraft that had the most spherical sphere ever created to try and measure some of the GR effects happening, general relativity effect, relativism effects happening in orbit around the Earth. And it was spot on. Everything has just been spot on. And that's, I think there might be something else that we're kind of missing. But yeah, I don't know. What do you, I mean, yeah, I think when people just start saying, well, we're missing X, I think there's something else we're missing. Like maybe there's a bunch of, I don't, now I'm getting really speculative. This is way outside of my actual expertise, but there's potential, for instance, for a bunch of naked singularities in all of the, gravitational space of the universe, right? So there's all sorts of extra ways that this extra mass could be accounted for. And the dark energy, I'm trying to think back to the things I've read, but so I don't know. I think GR seems to be pretty darn good.
It pretty much, the way the kind of direction that I was going was more of the coupling between, GR is fantastic in the regimes that we're dealing with, but when you talk about things going very fast at very small scales, that basically the joining of relativity and quantum mechanics, I'm wondering whether or not cosmological evidence will actually start to sort of clue us in on that.
Yeah, I think GRs, obviously there's aspects to GR that, when you start talking about small particles and things that are happening that are kind of outside of the realm, they definitely get outside of the GR just because of the size constraints. But I think that's kind of just like this fluid where, when you think about our, so this is kind of for everybody on the call, and you think about the different forces that we have, right? They just kind of happen on different scales, and so I think that, eventually what will happen, maybe it's 100 years, maybe it's 20 years, maybe it's 10 for some brilliant kid that's 22 right now, is, they'll figure out this theory that kind of is the composite of everything, and all of these others are little tiny sections of that one kind of composite theory, right? It's kind of the grand unified theory. And so for sure, there's areas in both energy and space, and there's all sorts of different cool effects that we can now prove scientifically that GR can't. It doesn't even really equate to, like, thinking about it from a GR perspective. I
see.
But yeah, but I think GR's kind of core core concepts and ideas are pretty concrete. I mean, like, for instance, okay, so here's a big one is, is there a flow of time, right? Kind of, is there cause and effect, right? If that was proved to not be real, then GR would be out the door. But I just don't think that we're going to really see that. There's always going to be, I think, a cause and effect. So in our universe, at least. So.
Oh, all right. I didn't really thought about that. So that's an interesting perspective. We do have a question from someone who might be related to you, an S. Baughman. What's the next step in your kind of research?
So the next step is just actually pretty quote unquote boring stuff, I would say, is we just going to look at more examples. This is kind of the slog of it. The fun stuff has already occurred, and now it's just more examples, finding out more data, getting more understanding of more examples, more examples, more data. So battling papers that contradict us, stuff like that. That's why I think to that first question, there's, contradictions occur in this great debate of the science community today. So there's nothing that like the science community thinks is firm unless it's been debated quite a bit. So
I would agree. We have one last question before we transition over to the telescope tour. It's actually by our tour guide, Andrew. He asks, what are your thoughts on Planck relics and or primordial black holes as kind of explain this, primordial black holes as a theory to explain dark matter?
Yeah. So again, I think that kind of stuff doesn't require new physics per se. The primordial black holes, and that's something that, again, James Webb Space Telescope, I'm hoping will especially since it's in the infrared. I think that's a great, obviously there was a lot of smart guys before me that decided that was a great telescope to go launch. When I was a part of the team, I was not part of the scientific team that was deciding on what they were going to research and what they were going to create as a observational capability. But I was connected to the actual creation of the mirrors. Actually, that was part of my group that helped work out, kind of those really. It's a really awesome mirror set. It's cool. So, but I guess to my point though is just simply, yes. Yeah, absolutely. I think that's exactly what I'm talking about. Is I think this is where observational astronomy is going to really help, and it exactly why, for instance, black hole physics has taken off. The core of black hole physics, right, was written by Wheeler, Thorne, and let me see this huge book. But but it wasn't until we have the observational astronomy to support the theoretical. They're both so important, so intertwined, and until you get the observational data, it's just guesswork. And I think that's part of the issue why people have certain issues with, like, for instance, string theory and some other of those, more quote unquote esoteric theories, is just because nobody's quite figure out how to like get observational proof of these things. And that was really way back, but now we've been able to prove that. So I do think, yes, sure. I'm curious, Dr. Parks, what's your quick answer as well? But yeah, I think that's exactly the point, is that better observational evidence is all we need to really understand the universe better at this point.
Yeah, I would agree with that. I think that I would definitely agree with that. There's a handshake between observational science and theoretical science, in that you have, I don't know where it starts, but you have, for example, observations, say, for example, Kepler, for example, he was able to observe that the planets go around in ellipses, and then Newton came along with theory and was able to explain what the physical underpinnings of that were. And then there are implications of that theory of Newtonian physics that then needed observational support in order to move forward. And so I would definitely agree with that there is an interchange between observational science and theoretical science, and you can't really progress without either of them. So in terms of the dark matter, my kind of feeling on it, it is well beyond my expertise, but what I've been being told is that the basically it's possibly neutrinos, that we're taught that the universe is swamped with these weakly interacting particles. So I guess I'm more on the WIMP side than the
You're for the WIMPs. Okay. So. Well, I'll buy you a beer sometime if it ends up being WIMPs. All right.
All right. Sounds good. Sounds good. Thank you, David, for the wonderful talk, and definitely the wonderful discussion afterward. If you'd like to stick around for the tour that we're about to give, feel free. If not, then I'll wish you a very good evening. And now I'm going to transition over to M, and he is going to provide us with a telescope tour of our observatory. And I believe it is now dark enough that we might be able to see something, and it's certainly clear enough for us to be able to see something.
Hopefully.
Hopefully.
Okay. To add on to Dr. Baughman research, so I also worked with Dr. Becker based on your research on this time lag. We try to model with a different kind of shape of the black hole in the transport equation. Yeah, hopefully I can get some reasonable data. Right now, I cannot produce that kind of time lag. Our model still cannot explain observational data. It requires some work on. Yeah.
Good luck.
So happy to see you.
Yeah.
Okay.
And thank you again for having me. And I hope that was the right level talk and everything else. And I don't know who's on the call, so I hope everybody appreciated it.
It's pretty good. Yeah.
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 Definitely.
So, okay. So now we're heading to the observatory tour part of the session. Right now, I'm sharing my screen, looking at 4 cameras attaching on different places in our observatory. As Dr. Parks mentioned at the beginning of the evening under the stars, we can see this silver dome from the outside of the research hall building. So this camera will record what's outside the dome, the tower, because we want to monitor how this dome rotates. And then we also have other cameras. For example, this one attaching inside the control room. The purpose of that is to monitor who's inside, who's operating. And sometimes we can use it to see what we write in the board. Maybe I cannot see it from my screen, but sometimes when people forget number, we can also refer it from the board. And then we also have 2 cameras inside the dome, and this is our telescope. So we place it inside so that we can see how telescope flew to the part of the sky we want, and 1 camera below this motor. So imagine that this is a fork. It looks like a U shape from this camera, but that it also has the base that connected to the motor. So this is the motor that rotates in right ascension direction. This is the motor that rotates the telescope in declination coordinates. And with these, we will be able to demonstrate to you how we operate virtually. Okay, so I'll begin with explaining our model of this telescope. So this is 32-inch Ritchie-Chritton Cassegrain telescope. So Cassegrain telescope is a type of reflecting telescope. It consists of 2 mirrors, 2 concave mirrors at the bottom, and so there's primary concave mirror at the bottom and secondary mirror at the end of this telescope. Light will comes in and reflect to the second mirror and then reflect to the tertiary mirror. And the Ritchie-Chritton is it's where the telescope is adjusted so that those concave mirror are in hyperbolic shape, so that we can cancel some of the aberration. Okay, I think I have the picture, the diagram shown here. This is what I just explained. So inside the telescope, we have secondary mirror that leads us to that reflect the light to tertiary mirror. I think I can rotate this telescope. So behind this part of the telescope, there's a camera. It's a CCD camera that works with a similar principle that that your camera phone works. And we also have an eyepiece. So tertiary mirror can be adjusted so that light can go to one of those devices. Okay, I think I will maybe turn this telescope a bit. Okay, so we have this program called SkyX. It's installed inside the computers in the control room. I think I forgot to explain that. We also have the computers in the control room so that tour guides and researchers can connect to this computer, like what I'm doing right now. I'm connected to the computer at the control room, and this will directly control the telescope using this program called SkyX. Okay, and here you see the current position of the telescope. I think I can, maybe I slew the telescope to Rigel, the bright star of Orion. So I can assign the position and then click slew. Here you can see our telescope move. So as it moves, now you should be able to see the Finder telescope. So this is it's like a small telescope with a wider field of view for observers inside the dome to find the target before using the eyepiece, because eyepiece has smaller field of view. So this is eyepiece, the small tube pointing downward here, and then our camera is blocked by the spectrograph, I think. And we can see the dome moves according to the telescope. Okay, we can see it move from the outside, but I think it's stopped now. Yeah, so the camera did not capture that, but anyway, right now it should be on Sirius. Okay, and to record the image of the sky, we use the program called Maxim DL. Okay, we will adjust the focus and then okay, so then we can also assign the filter, which will filter the light. So there's a filter view, I think it's somewhere in here. Filter view will select the light that comes into our camera. Then therefore we will have a specific wavelength recorded in our image. Okay. So right now I'll try, since we look at the star, I'll try red filter with try 1 second exposure. So this is the length of time that the camera should stay recording the image. The longer exposure time will give you the more intensity in the image. Okay, so here it is. This is Rigel. Rigel in the constellation Orion. So I think it's a white star. I can also show you I usually use this program to show you the night sky virtually. So if you look at the south, this will be about 45 degrees. Yeah, about 30 degrees altitude of the ground. I cannot click at the Rigel. Okay, so I think the next target I want to show you for this talk, since we focused on black holes and some galaxies, let's go to what is called Messier Object 66. So I click slew. Now telescope moves to the other side of the sky. So it took a while for this telescope to slew. So note that our telescope is using equatorial coordinates. So as I said, this is a motor for right ascension, and this motor is for declination. So when they move, they will select either of this coordinate first, and then move with the other coordinate. And we have this telescope setting so that the fork, so that the fork is pointing to the North Star, and so that the fork of the telescope, this axis of the telescope, aligned with the celestial pole, and that will benefit us when we want to track stars. The telescope will just move in one axis in the right ascension part. The declination will move just slightly in some case. Let's say if we track asteroid or planets or the moon, where its declination coordinate may change slightly. It will just adjust a little. But for the target like stars and galaxies, they almost stay at the same declination. So the telescope, you can just rotate in right ascension direction. Okay, so the fork just twists. Okay, and now we're pointing at M66, and you can see it from this camera. that the dome moves so that it has window aligned at the telescope. And we can see the telescope from the outside. And right here, you see a tiny secondary mirror. Okay, so let's take a photo of that galaxy. So M66 is a favorite galaxy. Let's try. Maybe I'll go with 1 second. So here I use the filter called H alpha. It's similar to red filter, but this H alpha is a specific wavelength produced by hydrogen atom. Ooh.
Yeah, you're going to need far longer than 1 second exposure to get that. I would try probably 30 seconds at the very least.
Okay.
Because this is a dim object and that filter is very narrow, so you're not getting a lot of light.
Okay.
More light than you would get in the X-rays, but still not a lot of light.
Yeah, I think the magnitude is around 8, 9 actually. Yeah. So it's pretty faint, but I selected it because I believe that messy objects should be bright enough for some light, some sky conditions.
I think you're very right about that.
Yeah, so this galaxy is in the constellation of Leo. It's one of the group of galaxies called Leo Triplet. So there's M66, M65, and NGC, which is New General Catalog, 36, 28. I think I can show you. Oh.
Might want to try a 30-second in red.
Okay. While we're waiting, I can show you virtually on this screen. So it's this part of the sky. Actually, I think I may want to get rid of. I have lagging issue in my computer. Okay, so I'll get rid of the atmosphere. So it should look like this. This is according to the program Stellarium. I believe this, yeah, M65, and this is Hamburger Galaxy, MGC 36, 28. So those three are in the same group, they're in the same neighborhood. And I choose this because according to our talk, this is a Seyfert Galaxy. Seyfert Galaxy is a galaxy that produces a specific specific radiation at the core. It can be Seyfert 1 galaxy or Seyfert 2. Seyfert 1 will produce UV, some X-ray, I believe, at the core, and Seyfert 2 will produce much in infrared at the core. Okay, so here is the picture of that. So we can see a slight bar or spiral each shape from this. Okay. Okay, try.
think we might need to get photo to image this. I don't think we've looked at this before.
Yeah. Okay. So yeah, so that looks like a bar and spiral, just a blurry spiral. If we wait long enough exposure, and I think if we have darker sky, maybe we can have that. Okay, so I will hand over this to Andrew. He will explain to you, he will introduce you some more galaxies. And if we cannot capture using our camera, we can also show you some pre-recorded picture from our archive. Okay.
All right, thank you, Em. I'm going to try to now look up and slew to M106 Galaxy. Let's see how that works. Okay, and M106 is relatively, it's a similar distance. It's like 22 to 25 million light years away compared to the M60 Galaxy. So I think we might be able to do 30 to 45 second exposure. How does that sound?
What was the close end of that? Something in 60?
Oh, should we just do 30 to 45 second exposure for this one as well?
Yeah, I would do a 30, see how it looks, and then if we don't really see much detail, then go up to 45.
Okay. Actually, yeah, let's do that. Okay. So this image is going to take a while to process, so I'll just talk a little bit about the galaxy. So M106 Galaxy, as I mentioned, it's about 22 to 25 million light years away. And it's also a spiral and a Seyfert galaxy. So spiral galaxies, like our galaxies, are the ones with the large spiraling arms. And the way that happens is that early in a galaxy's formation, when a lot of hot gases and stars and other material circles around the galaxy, it takes increasingly longer to do one full rotation as you get further away from the center of mass. So the end result is a spiral formation over time. So that's what spiral galaxies such as this one, and that's how they form. And this one is also a Seyfert galaxy, which means that it has an active galactic nuclei. So active galactic nuclei are galaxies with supermassive black holes in the center, and they continuously, they have a very hot accretion disk and continuous amount of gases and things like that flowing into it until until energy basically gets compiled and released through these large jets periodically. And that's caused by the compression of the gases and the heat and the sheer amount of energy occupying one space. So, was this the same image right here as earlier?
Pull it down.
I think. Oh no, this is the new one.
Yeah, I think so.
Okay.
Oh wow, yeah.
Oh, that doesn't look too bad. So we can see the bright center. And this is a relatively large galaxy, so I don't know if that has anything to do with why we can see it so well besides the exposure time and everything. It's about the similar in size to the Andromeda Galaxy, which is 220,000 light years across. And our galaxy, for comparison, for reference, is about 100,000 light years across, so it's almost twice as large. But this galaxy is also much, much further away. And I also just wanted to add a few points about black holes as well and galaxy formations in general, just because that was a part of the talk today. There is a theory on what dark matter could be, and right now it's inconclusive, but there is a theory that primordial black holes are responsible for creating a lot of the mass in galaxies, and that could be what dark matter is. And the way this was proposed is the fact that uh, there's a lot of unaccounted mass, or I guess maybe gravity behaves differently, or we're not sure how these galaxies form relative to how we know gravity behaves on those large scales from simulations, from from simulations like physics simulations and things like that, uh, uh, simulated by supercomputers. So that is one of the theories, is primordial black holes. And basically the theory is that when the Big Bang occurred, or something similar to it, and the universe expanded very rapidly, there were regions of matter, of denser regions of matter relative to other ones, and these could have collapsed into black holes. And over time, these black holes would have slowly dissipated to different sizes, some of them extremely small. Um, and that's why I mentioned in one of my questions earlier um, uh, about Planck relics. Those are extremely small Planck-sized black holes. Not sure if they could exist, or if they do, they would have been larger at once, but these would be very dense objects, and it would make sense as well if they do exist, because they aren't really detectable by current tech. So LIGO, which is a facility that detects gravitational waves, can only detect very large black hole mergers. And back in 2015, when one of the black hole mergers was detected, it was extrapolated that it would have been much larger in size earlier in the universe. And the only way it could have reached that size was, or I'm sorry, the only way it could have reached that size if it was from much earlier in the universe. So the theory is that these could be scattered all around the universe, not detectable by current means, could be the reason for, or actually that could be what dark matter is, and it's giving that extra mass that's unexplainable. But there are a lot of things against this theory as well. So that is why a lot of scientists that they look to people tend to look to trying to figure out what other new particles there are, or maybe new particle behaviors by sifting through data at particle accelerators and colliders. So it's pretty inconclusive right now, but it's pretty cool area of research right now. If any of you want to look into it more, there's actually a YouTube channel. His name is Anton Petrov, and he does a lot of detailed videos and also posts scholarly articles and all the experiments and direct research in his links too. So that's where I got all this information from, and it's all legitimate data. So if you're curious, you can look into that as well. So that is a little bit of information on galaxies and black holes in general for that aspect. But now let's take a look at another galaxy. Let's see if it's in the sky, M81. Okay. Oops. There we go.
One thing I will say about this image up here with this galaxy, it seems to me that you have the bulge in the center of the galaxy, and then you have these very large spiral arms, these two spiral arms that are coming off the top of the galaxy and then the bottom of the galaxy as we observe it. So there are three different types of galaxies that we that we know of, or at least classify. And these are spiral galaxies, which have spiral arms. They have basically a core or bulge in the center of them, and then they have these spiral structures of stars and gas and dust within them that come off that central bulge. Then we have elliptical galaxies, which, as the name would imply, look elliptical. They primarily are featureless. They're primarily smooth, and they really are just really, they are what we refer to as red and dead. They have very old stars. All of the massive blue stars are pretty much done, or pretty much have evolved and died and actually formed small black holes of their own, stellar mass black holes of their own. And then you have irregular galaxies, which, as again the name would imply, no two irregular galaxies look similar. And so you have that. Then you have M81, which I will let Andrew, but M81 is an elliptical galaxy. But take it away, Andrew. Sorry.
Oh, no, thank you, Dr. Parks. So this one is M81. This is an elliptical galaxy that is about 90,000 light years across and about 12 million light years away. So a little bit closer than the past galaxy, but this is also quite small. Not too much smaller than our own galaxy, which is about 100,000 light years away, light years across, but this one is a little bit smaller. Elliptical galaxies, they form quite differently than spiral galaxies. I do know that elliptical galaxies, I believe they form as a result of collisions or interactions with other galaxies, which causes the spiral arms to not form, or if they once had a formation, it would disrupt that formation and cause this irregular shape. Well, that would be irregular galaxies, but this elliptical galaxy is smaller in general, just because they were once part of a larger galaxy and then they broke away, versus irregular galaxies tend to be extremely large and are a result of a lot of different gases disrupting each other and coming together. So there's not a consistent formation going on. And this is also a active galaxy, so it has a active galactic nuclei in the center. It's too saturated to see, but this is the general image of the galaxy. Does anybody have a question on any of these galaxies?
I will point out that there are giant elliptical galaxies, because there is a phenomenon which we lovingly refer to as galactic cannibalism. While stars don't interact with each other too very often, because the distances between them are far larger than the sizes of the stars themselves, galaxies are not so much. The galaxies are, on general, are much larger, or large enough that the distance between the two nearby galaxies is such that the gravitational pull between them can cause them to interact and actually, well, eat each other. The Andromeda Galaxy and the Milky Way Galaxy are going to do this in about 4 billion years or so. And when they do, simulations have shown that no matter what you start off with, either a spiral galaxy and a spiral galaxy and elliptical galaxies, and obviously two elliptical galaxies, you smash them together, ultimately you're going to get an elliptical galaxy at the very end of it. Intermediate to that, you're going to get these irregular galaxies. A lot of irregular galaxies that we see are essentially the merger of two galaxies in the process of merging them. Like the antenna galaxy is the sort of the best example that I can think of off the top of my head of two galaxies that are currently in the process of merging and basically throwing off these large streams of stars. So if you're curious, I would highly recommend Googling the antenna nebulae. Hubble has taken a beautiful image of that. So yeah, I just wanted to put that out there.
All right, thank you, Dr. Parks. So I don't if anybody has any questions, please mention in the chat, or you can turn on the speaker to voice your question. But other than that, that's all I really have for this galaxy. Do you guys Rob and M, do you suggest we look at another image?
Let's see, what time are we at now?
It is at it's 8:40.
I think we can wrap it up at this point. We've
Okay.
gone about an hour and a half. So unless there are specific something specific, something specific that people in the audience would like to see, I think we can again thank our speaker, Dr. Baughman, and just basically wrap up and sign off. All right. Again, thank you all for coming. I very much appreciate any audience that we see or any audience that we have, and I highly encourage you to come back again in April for our last two Evening Under the Stars this semester. Again, we'll have interesting talks from a variety of speakers, and we will again do a telescope tour. And every telescope tour is different. We tend to try to mix things up and look at different objects, trying to match up with what the speaker has to say or talked about. There seems to be one question. What is the proper name and object type of the galaxy? The one we just viewed is M81 or Messier 81, and it is an elliptical galaxy.
Yeah, so the one that I talked is M66. It's a spiral galaxy.
All right. I bid you all farewell. Again, thank you for coming and have a good evening.
Have a good one, everyone.
Good night.
See you. Bye.